problem that looks for power, which is how quickly energy is done. Here's a problem that wants to solve for power, which is the rate at which work is done. And they're asking to solve for power in a real-life situation. It goes like this. Jack runs up the stairs, elevating his 50-kilogram body a vertical distance of 10 meters in a time of 20 seconds. Determine the power done by the stairs on Jack's body. In other words, how quickly is the energy changing? What's the power output involved in this? So with any situation, I want to draw a picture, see what's happening, and put some information on that picture. To begin with, let's say Jack's right there, just kind of waiting, about to run the stairs. And then here are the stairs Jack's running up. Wow, they look big relative to Jack. And then here he is at the end, just waiting around again. The other thing we know is that this vertical height, this vertical displacement here, is 10 meters. So if we want, we can define ground level wherever we want, but if we want to say that the place where Jack starts, right here, has a height of 0 meters, that's fine, but then we say the place where Jack ends has a height of 10 meters. It doesn't really matter where you define ground, but it's nice one place, the lowest place in your problem, happens to be ground level, or height equals 0. Okay, so we got our picture, we got our information, we're looking for power. Power is how quickly energy is transformed, the change of energy per time. Or in other words, it's the work done per time. Work, just to give you a little more information, is the product of force and displacement, where they're parallel to each other. And so one option for this problem might be to try and find the average force and the displacement and look at that. You can assume things like he's running up at a constant speed, so the up force balances the down force. It gets a little messy. So probably the easier method might be to look at the change to energy rather than looking at force and displacement. Either's fine. This might just save you a little work, if you will. Alright, so let's look at the change to energy. So we're looking at from the beginning situation to the ending situation, how much the energy changed by. At the beginning, maybe he has potential energy, maybe he has kinetic energy, and we call the total of the two TME, total mechanical energy. Potential energy is stored energy due to position or condition. Kinetic energy is energy due to motion. And at the end, you might have those things as well. So here he is at the end. You might have potential, you might have kinetic, and you might have total energy. And so let's just fill in as much as we can. At the beginning, we defined this to be no height, and potential energy is mgh, mass, 50 kilograms, has the acceleration of gravity, 9.8 meters per second on Earth, times height, which we defined as 0. So again, that's kind of easy to define one place as 0 because then there's no potential energy to start with. Kinetic energy, that's a half times mass times velocity squared. He's not moving at the beginning. So his kinetic energy is 0 to begin with. So we can say his total energy is 0 to begin with based on our definitions and assumptions, 0 joules. At the end, however, it's not true. He might still not be moving. I mean, he might get to the top and stop moving. In fact, let's assume that. Let's say he's not moving at the top. He moved in the middle, but not at the top. So let's say that his kinetic energy is 0. But what has changed from the beginning to the end is his potential energy, his stored energy because of position. He's at a higher position. There's more energy stored as a result of that. So if we calculate his potential energy at the end, we use his mass, we use the acceleration due to gravity, and we'll use the fact that he's now at a height of 10 meters. And his potential energy at the end is 4,900 joules. So the total energy at the end is 4,900. Okay, so we're really close now. We were looking for power. Power is change to energy per time. And we can see that the final energy is 4,900. The initial energy is 0. So to find the total, we're just going to subtract the two. We can do that in our head. 4,900 minus 0 is 4,900. So we can go ahead and sub that in. Power is change in energy over time. We just said the change in energy is 4,900 joules. And the time it took to change that energy is 20 seconds. So in the end, that's a power output of 245 joules per second, which is the same thing as watts. So Jack's managed to change his energy by 245 joules per second on average.